Thank you. So, is everyone happy to be here? I am. So this talk is about Eve and the service of Eve and how we managed to keep it on a single shard. So it's you probably all know about this game. One world, one cluster, that was the original design goal. And we've managed to keep it that way, more or less. Growth has been steady with some slight hiccups once in a while. But fortunately, hardware and design and so on has kept up with population growth. We are always growing. We are now at 360,000 players that regularly play with the maximum concurrent user use. Those are fairly recent figures, 60,000 somewhat and something people. And 60,000 people playing online in the same universe at the same time is a lot of people. This is 60,000 people. You don't see all of them. 60,000 people, if they queue up to buy something in a bakery, would stretch for 30 kilometers. So it's a lot of people. And why do we want so many people? Well, that is because of the value that many people have over few people. So basically, as more people connect, the network that they build becomes more complicated. So the value of the network grows exponentially with the number of people. So we firmly believe that with 300,000 subscribers that we have a network that is much, much more valuable than 50,000 people. Size matters in this game. Now we have something called Eve China. This was launched in 2006. This is a special server that's dedicated to China. It is much smaller than TQ, so it doesn't face the same technical challenges as the great Eve International. So this talk is about Eve International. Now, just at the beginning, I want to point you at the eveonline.com website. There is also lots of information about Eve in the Eon magazine, which is a community-driven magazine written by the players themselves and is the official magazine sponsored and endorsed by CCP. Now, there's a lot to talk about in a talk like this. There are so many ways that enable us to do this. We have to be a little bit selective about all the stuff that we're going to cover. So basically, what I will do is take, well, 3 or 4 technologies that we think, or methods and aspects of operating Eve that we think is crucial in keeping everything on a single server shard. So some of this is overly complex, and we don't want to get too deep into details, but I will show some, hopefully some actual insights, and there will be hopefully a live demo. I was going to have an internet demo as well, but that's not going to be possible because of internet restrictions. And reference material at the end. Now here is what we're going to cover. We're going to look at the database system. This is the heart of Eve Online. And how we use that. We're going to look at stackless Python, another key technology that we have embraced and has enabled us to produce copious amounts of code and working software. Destiny is our space simulation software. This is also crucial in enabling 60,000 people to interact in spaceships. And we're going to take look at the hardware configuration of the server cluster itself. Before we dive in, just to clarify for you a brief overview of the cluster architecture of EVE Online. You may have seen this picture before. We've been using it for 10 years, I suppose. So this is the sort of grand overview of the server. There is one SQL server in the middle. That's the center of everything. Around that, we have the soul nodes, as we call them. These are the game nodes that serve and run the game logic itself. There are currently 52 IBM blades in the array, and on these 52 blades we run over 200 soul nodes. So we run 4 processors on each of the nodes. Around that and facing the customer finally are the proxy nodes. We have 27 of these on 10 blades, and their role is to direct traffic and information from the user to the appropriate soul node. Now, let's talk about the database. Game content, everything basically is in the database. It's the foundation of everything, and it is a crucial aspect of it. Managing the database is a huge operation in itself. What is stored in the database? Well, we have game content. That's the layout of the universe, ship types, weapons, data about weapons, everything like that. We have the market system, everything related to trading, every object, where it is, how much it costs, all the agents that buy and sell. These are game elements as well. Inventory of objects, inventory of people, what objects do people have. Basically, the entire game state is there. Ship positions and stuff like that, even during space combat. And in addition to the game state, the database is intensively used for logging of all kinds of things, like, for example, what happens during a battle, or what kind of stuff changes in the inventory. This is used by the game, of course, the GMs to settle all kinds of disputes. And as you see, it's huge. I mean, this is 1.4 terabytes, and this number, 2,000 number of transactions per second, is pretty high. So we have had to use state-of-the-art hardware to do this. So 10 million insertion in a day into the items table. This items table is the central table of the inventory system. So because of this, we require an enterprise-level database. It just has to be a pro machine to handle the load. So we have SQL server. We have settled on Microsoft. We have used Microsoft SQL Server since the beginning, and it works well for us. There are all kinds of reasons for this. We had a close relationship with Microsoft, and we also, I will go into that later, the software interface to the database is very good when we use this particular one. The brick server, all the RAM, the CPUs, I mean, this is just throwing hardware at a pretty difficult problem. You notice the latest 2 points, the Ramsan. These are solid-state disk drives and a non-solid one. When these were introduced a few years ago, they really helped us push the boundary of the database, because I/O to the disk was a bottleneck. So we don't have that anymore. Now, to run this, and this crucial part of the game, we need enterprise-level DB engineers. I mean, we have lots of people that are really, really smart, that work day and night on making sure that the database is running smoothly. And this is everything from, making sure that if something breaks, that we can fall back to a functioning copy. We do have hardware problems, so we have to fail over and so on. And because this is a central part of the cluster, when it fails, it can be critically bad for everything. So making sure that it just runs is one thing. And then, of course, designing the application that runs on top of it. Tables and procedures. I mean, we are professionals doing this. We're all professionals, really, but these are incredibly important ones. we have engineers monitoring how we use the database, both the backend, just looking at the database own logs, but also application level logging. And sometimes we see something strange going on, and an engineer will say, why are we doing this so much? And these kinds of changes, they end up often in game design. And a game designer will say, well, we have to stop using these kinds of weapons because, or at least modify the way that they work, because the database can't cope. Or rather, if we did it the other way, we'd be able to save so and so much on the DB. Finally, I put in a point here about something called branch static data. There's a lot of game content that's stored in the database. Authoring of game content is done directly on a copy of the database. And since we work in many development branches, we have to make sure that these copies of the designed content are also reflected in a branched view inside the database. So we have a fairly complete system of revision control of game content in the database. This is also something that's been designed by our database engineers. So from the application's point of view, we use stored procedures for everything. They are handcrafted by database engineers. So these are the best of the best. And this involves the lowest possible runtime cost. All DB logic is put on a single place in a source repository. We can just take a look at all the SQL code in one place. And it also simplifies monitoring, because you don't have ad hoc SQL going over, but rather you have named procedures doing certain things, and you can see what they're doing. So, for example, if you have a procedure called, upgrade weapons cache, and that's taking, a few milliseconds, then an engineer knows that there's something wrong with the weapons upgrade cache thing. This model integrates very well with Python, that I'm going to come and visit a little bit later. The way that we program this looks like a synchronous function call from the programmer's point of view, and we return optimized data structures. Here's just to give you an idea of what we might look at is, for example, a report. We can go into the end. Sorry, this slide is not available in Chinese. We can go and visit the backend service and ask them, what's been going on in the database, and it will spew out something like this. Basically, here is a report on the number of stored procedures calls made in a 13-hour period, and we can see, we spent so and so much time on clue get client by character. So this is all very informative and can help us run the system. Now here's just for your information, example code. This code is actually from the web server, the web backend. No, that's not right. It's actually from something else, from GameLogic. But it just shows how an application programmer uses the database. He just writes his application function in Python, and then he has this single function call here. Let's just look at a function call. It's calling the stored proc context prime, and it gets the rosette right away, and it iterates over it. You notice down here that what the programmer can do is call the above function on a tasklet, and we will come to this later. But from the programmer's point of view, this is imperative programming. He's just doing this stuff, but it all executes in parallel and is thus very scalable. Now, which brings us to Python. Back when we were designing Eve, we had to decide on how to do it. We were few people. We had a massive project. We were going to create a space game with thousands of people playing, and there were some 10 of us, and we didn't know how to begin. We had some nice graphics. We had some cool rendering engine and great concepts, but how can we create all this massive code? And we rationally just thought, well, we need a powerful language. We started looking at all of the scripting languages that were available on Windows. We had done experiments. We had running prototypes using NC Fibers. But one of the early engineers that worked with us stumbled on this thing called Python. And what's more, he found stackless Python immediately at the point. Stackless Python was something that was going on and was very cool, and I'll come to that. But as long as we had Python, when we had it and had done experiments with it, we knew this is the language that's going to give us the expressivity and the power to create this game. So, probably all of you are familiar with it. It's not very often used in games because it's rather large and it can be a nuisance to integrate it into applications. Python is designed to be a standalone programming language, and it has its roots in Unix. So to adapt it to something that's like a game and embed it, it can be a little bit daunting. But we've done it anyway, and it's not impossible, and it's actually quite easy if you ask me. But anyway, it is this simple language that is easy to learn and has incredibly rapid programming power. We have taken game designers and said, why don't you stop whining and asking for features? Sit down before the computer, and this is Python, this is code that works, now do like this. And in a few weeks, these guys are application-level programmers. They just learn the program by looking at it. It is intuitive syntax, and we have interactive development cycle. You can have the game actually running. You can edit lines of code. It will be reloaded into the running program, and you can see the effects on the running program. This is enormously productive and incredibly powerful. So if you don't know Python, you should. But what is stackless Python? So a very clever German guy called Christian Tismer decided that Python was incorrectly done. He said, no, you're doing it all wrong. You shouldn't be using the stack. You should be doing it this way. So he went to his basement and wrote a different core engine for Python called stackless Python. And it never went mainstream, but it is a very large and stable branch of Python. What it gives you is parallel execution of execution contexts. When I say parallel, I don't mean thread parallel because sadly Python is single-threaded, but it gives you logical execution contexts. We have so-called tasklets, which are like microthreads. So it enables us to have lots of logical tasks going on. And with the proper libraries for input-output, like talking to the database and proper networking libraries, you can use your good old imperative procedural programming model to do all the massively parallel I/O that you need to do in a parallel game like this. So traditionally, if you were doing this with handling, for example, 30,000 client connections, you would have some sort of an event-driven callback mechanism. We don't do this here. We just write the program that reads user input, performs this action, writes user output. So this really allows you to be more expressive in your code, and it removes a layer of complexity that's often involved in writing I/O that's based on this kind of stuff. So what's more, this particular version uses stack slicing to achieve the parallel execution of stackless. You could switch from one task to another, even if it's not Python code, even if it's C code, because it uses stack slicing. It cuts the stack away and replaces it with a different stack. And this is pretty interesting technology. So they are execution contexts, these tasklets. We can have tens of thousands, hundreds of thousands of active tasklets. When I mean active, I mean that they are not actually working, but they're waiting. For example, reading a network packet or something. They're just dormant until something happens. You can't have this many threads. It's impossible, both because in 32-bit memory space, if you're using that, each thread consumes so much virtual memory that you will die if you have more than 100 threads or something. Also, threads, they they consume operating system resources when they're not being used and so on. The cool thing about tasklets is also that they are cooperatively switched. When a tasklet is running, it switches to another tasklet at a known point. It's not like when you're doing multi-threaded, where you're running something and suddenly the operating system may let this thread run, which will force you to have all kinds of locking and stuff going on because you never know what's going to happen. You don't have this particular problem when you're in tasklets. So there's almost no need for locks, except for objects that have some sort of shared state that's being modified by many tasklets. Certain I/O code and so on, but application level code usually never has any locking, and it works just fine. As I said, with C extensions being switchable, this means, for example, that we can write our database access layer that translates Microsoft SQL into Python in such a way that it works with tasklets and gives us this transparent magical boundary where we just call a remote procedure call. It will suspend the tasklet while this thing is going on. It will reawaken it when data comes back. ，So here is.
那么现在在这里看到呢，这是我们的一个代码的例子。这个呢，就是我们怎么样用这样的一个起始的编程的语句进行这样的小任务的设置。你可以看到，这有2个操作在这里。那如果你要看到这一个 CPU 的这个图形呢，你可以看到这一个线程。那么同时我们也有这个遥控的对象，我们用我们的这个跟我们的远程的服务器进行交互，同时也有一个是 debug 服务器。我们一般在这个应用的编程里面呢不去做的，但是呢在这里呢我们有用到，因为呢这样子看上去是比较的直观。我们除去了这一个远程的编码之后，加上这个 Python 的编码之后呢，你看到这样子你就可以进行一个调制。那么当这一个呢你在把它给应用起来的时候呢，你就可以看到这个信息呢能够直接的发送到 socket。当这一个编码实行的时候呢，它还可以延展。那么同时呢，能够重新的被呼醒。那在这样的一个固定的功能里面，固定的函数里面呢，是可以有所呈现。那么因为呢是非常的有用的一个语言呢，所以我在这里呢给大家再展示另外的一个例子。在这里我只要只是写一个很简单的2个简单的小任务 tasklet 的代码，在这边给大家看一下。不好意思，我的这个键盘有点不好用啊，那我调整一下。好了，我已经写完了这一段代码了。那么这里呢是有2个 tasklet， 把它2个绑定在这一个函数里面。 那么我在写好这一段呢，我就可以去让这一段代码呢去运行了。好了，你看就成了。你可以把这一个记在你的笔记本上，我不会介意的，大家可以作为一个参考。这就是一个很小的例子，那这是一个我们运用的一个脚本的语言。我们同时其实还我们可能在实际运用的时候呢，还会将这个语言进一步的简化。那这就是我们在工作上面在写编码上面的心得。但是有人说对，你说很简单，但是呢
lots of things like a jet airplane and a milk truck, but it's fast enough. And you have to remember that it's 80% of the time you're running 20% of the code and all the various perturbations of that particular logic. It turns out that the performance of most of your code is not important. It's very small parts of the code that actually carry the brunt of your game. And all the other code is infrastructure, is logic that isn't really that performance critical. You can very well afford to have code that contributes only 10% to the runtime of your entire project to be twice as slow. Okay, maybe you can't afford that, but if it were even slower, you see, it's all relative. So you have to balance, where do we want to put our programming effort? And we decided that development performance is just as important as the runtime performance of the application. Because hardware is cheaper than developers. And it scales better. You can't make a project twice as fast by hiring twice as many programmers. But you can buy more CPU. So this is the approach that we've taken, and it is proven to be, we've been proving right, more or less, I would say. We have performance critical points of the game. We have the space simulation, we have the rendering engine, we have the database layer, we have the networking layer. These have been hand optimized and written in C. But we haven't even started looking at assembler. We've found that just focusing optimization down the right track after we develop our prototype model, that way we get the performance that we want. Now, a stackless Python is even cooler than Python because the human mind isn't designed for event-driven logic. Event-driven programming has given birth to whole frameworks to try to somehow make the event-driven model easier to understand. But it's trying to, improve. If you have a can of worms, it's no better if you have a great can opener. You should just not have a can of worms. So there is a framework called Twisted, and this is very apt. This is a Python framework for doing I/O, event-based I/O, and it is Twisted. Whereas this is the world with stackless Python. So I'm going to show you a short movie now. This movie is from last year. It's called The Butterfly Effect, and it explains a little bit the value of having such a large universe and what can happen if you have all these players interacting. Come on.
In chaos theory, there's a concept known as sensitive dependence on initial conditions. Most people call it the butterfly effect. In Eve, we call it the sandbox. Let's say this is you. One lone wolf flying a starship in the far reaches of space. And in your travels, you encounter this. A defenseless mining barge under attack by pirates. You have a split second to make a choice. Without your help, the miner doesn't stand a chance. You decide to be the hero and succeed in driving the raiders away. The victim is thankful, and in the conversation that follows, a friendly gang that was on its way to help finally arrives. Grateful for your assistance, they invite you to fly with them. As it turns out, that gang was on its way to regroup with more patrols, who are all members of the same corporation, which happens to be part of an alliance of corporations that is currently at war with another alliance, whose patrols have just spotted the one you're flying with right now. Your decision to help that miner led to this moment, an epic battle between thousands of players, and the chance to share that experience with new friends that you might have for the rest of your life. Hundreds of thousands of people could hear about this battle. Why so many? Because it all happened in one universe, not in separate realms, just one big sandbox, where the actions of one person can resonate throughout the entire game world. In EVE, the choices you make shape the outcome of events. You could have helped those pirates, or just flown on by. What matters most is that the experience was emergent, unscripted, because in the sandbox, all player actions, no matter how subtle or bold, always have an impact. Imagine what you could become a part of. Being in the right place, at the right time, could touch the lives of more than 300,000 people in 230 countries around the world. Welcome to EVE Online. The universe is yours.
Okay, so we're halfway through. I'm now going to talk about Destiny. And Destiny is the name of our physics simulation engine. We have to talk about, EVE is in space, obviously, and there's a lot of space things going on, and the simulation of this happens in this engine called Destiny. This is one of the parts of the game that's handcrafted in C. And I'm briefly going to explain to you how this works and how we partition the problem that we face of having tens of thousands of people into a smaller problem that's actually solvable on a computer. So we have dynamic space partitioning that tries to partition space into causality bubbles. The simulation is deterministic, and this allows us to run the simulation in parallel on the server and also on the client. The server runs a simulation that is the authoritative one. It has truth. The client runs a simulation that's an approximation of the truth, but it is identical in any way if there is no discrepancy between the initial conditions. So this is basically a computing engine that evaluates differential equations. The hierarchical space partitioning simplifies the problem of transforming the entire state of the entire universe into the sum of smaller transformations. So it turns a problem that's an order of n squared problem into, ideally, an order n problem. So here's a simplified sort of picture of that using tensor notation. You will notice that some of these bubbles causality bubbles have many objects. One may have just a single object. It gets more complicated when objects collide, because objects have velocity. So in our simplified model of spaceflight, objects, they travel on a straight curve or under a fixed force. And we have exact solutions to the motion equations that occur during this. And what we had to solve for was then how do balls collide. Ships are modeled as being elastic balls. And anything else would be too complicated to model, of course. But then we have these collisions that are when cylinders intersect. And we have to compute the elastic collision response. So we set up this model, relatively simple, and set out to solve it, and we solved it. There's a physicist working with us who spent some time on doing this. So this is what you see before you is the spaceflight equations used in Eve. Yes, you can take a picture of this if you want. So, but it is an algebraic solution, and that makes it possible to have those simulations running on the server and the client, because it makes the problem insensitive to the length of the timestamps and other sort of things that can fuddle the field. So just a brief overview of how it works. The server is resolving, of course, the entire system. By system we mean a solar system. The client has only to worry about that which is in his immediate vicinity, his own causality bubble. This makes the problem easier for the client. The server then sends updates regularly to the client and tells it, if things have changed. For example, if ships have entered his causality bubble, or if they have left, and how they are traveling, and so on. So this will allow the client to actually jump back and recompute if it needs to. So, and here we start thinking about scalability. Client scalability and client CPU effort is related to how many other clients are in his same causality bubble. A server has to deal with more information. It has to deal with the entire system. As I say system here in quotes because it depends a little bit on what we mean. Traditionally, we would solve the problem for an entire solar system, but now we can actually partition it into smaller entities, own sort of causality bubbles, as long as ships are not traveling directly between them. So this brings us to the Eve universe. So this is an artificial galaxy, if you want, of 5,000 solar systems. This was created in the outset. Just before Eve was launched back in 2003, we decided, well, now we need to generate this world. So we ran the simulation then. We have solar systems that are connected to each other via routes, and they then build bigger entities that we call constellations that again become regions. And these regions then together are the entire world. Solar systems were modeled. They're typically very Earth-like, or they're based on what we thought back then, and I think even now that solar systems are something that is created out of a mass of dust and particles, and it sort of conglomerates into a sun and some spinning planets with moons. So we computed them in 24 hours. But then we have to think about the large-scale design of the universe. And because the routes are what makes it interesting, it's the connection of planets that's really important. So first and foremost, to create a universe, we have to detect how do planets connect. Their absolute positions are secondary, but the connection properties are the important ones. Because the routes are so important, because they have tactical value and strategic value. They define areas that you can conquer. They define corridors where there's lots of trade, and so on and so forth. And to do this, to create this simulation, we ran a model called diffusion limited aggregation. This is a mathematical model used in network analysis in many other fields to simulate how complex molecules and other organic structures grow. What's done usually is that you place a seed somewhere, and then you have another object randomly walk towards it, and at some point it sticks to the other object. And then you add more and more particles. They tend to go and stick to the other one. And this creates very interesting fractal patterns. You see here that this has actually a reflection on what we have in real life. This is a gold colloid aggregate. This is a gold particle that is formed in a similar way. And we wanted something like this. And this is what we ended up with. Having run the simulation and created the Eve universe, we got this tangled mass of roots. So now we know how to create solar systems and how to create universes. But this all has implications on scalability. As we, in our original design, and still now, the smallest unit of scaling is a solar system. This is not exactly true. We can still take things out of a solar system like a space station or something and deal with it separately. But this is still the sort of physically smallest point of scaling of the software problem. And this has problems because some systems are very busy. There is a legendary system in Eve called Dita that we're constantly fighting to make it run smoothly because there are so many players in there trading, because it's conveniently located. And this is just something that fell out of the simulation. To deal with this problem, we obviously make the code faster, but we've also done other things like making the system less desirable. And how do you do that? Well, one thing is you can change routes. You can change the solar system. You have to, of course, do that in some gameplay-related manner, like saying, oh, there was some astromechanical crash of a Stargate or something like that, or there's a disturbance in the force. But that's possible. And this is something that needs tweaking. The game has been running with an unchanged, more or less, world for 7 years. And obviously we have the power to do anything. So we just flip bits in the database when we need to. But we want to scale with increased hardware. So this is basically where scalability of Eve has fortuitously sort of emerged. We have a software architecture that is scalable because the game that we simulation is inherently granular. So we have this layer or these two dimensions in software and in the hardware that make it scalable. We have scalability through the tiered architecture of the software. We have the database down here. We have sol nodes solving particular problems, which is the game logic, and we have proxy nodes doing the routing of user traffic, which is more a managerial role. But then we have also the granularity part of the architecture, which is that the problem is inherently such that we can split it into sub-problems. We can take the market and run it there, and we can take the space station and run it there, and so forth. And by splitting up the problem like this, and making maximum use of the technology I already showed you, the database, of having the worker threads run and having the stackless I/O completion ports, Python logic, all that running, we are able to scale. Again, I'm going to just show you the tiered architecture, the role of the proxies in here. Here we have, again, this cluster going on. But what the proxies do is that they route the traffic. As you see, there may be something happening for this user, and he needs to send a message to this guy. So the proxy will, in that case, circumvent the entire Sol nodes and just send it directly over to this guy over here. On the other hand, if this guy is doing something that involves the market that's running on this Sol node, it will be directed over here. Now, this is how we can split up the problem. We can split up the solar systems into smaller entities, but we start out with the solar systems. We can take the space station out of this. We could take services, special services like the market service that runs within a region, and we can run that on a separate node, thus taking load off a Sol node and having a dedicated market node. Cooperation services, proxy services, all kinds of game logic services can be taken out of the game and put somewhere else. But we admittedly have the problem of the solar system still being sort of the smallest granularity, and we're working on ways to make it more granular. But doing stuff like this, we can essentially just buy more hardware. And if we grow, we can still buy more hardware. And essentially, if we manage to have everything the software as granular as possible, then there's no problem buying more hardware and solving the scalability problem. Currently, we have grown Eve so that the server is essentially a supercomputer. It's hosted in London and is an IBM Blade Center. We have some 200 active servers, and we have some 7.5 teraflops going on. The bandwidth towards the user is 400 megabits. So this is a pretty powerful machine that we have there. So we're drawing towards the close here, and so I just want to summarize the points that I've been trying to make here. How to make sure that you can have an application that's as big as ours or even bigger and be able to grow it. You have to start by structuring your application from the outset in ways that promote scalability. You have to think about granularity. You have to split up the problem. Try to design your game idea in such a way that not everyone is interacting with everyone at the same time, but maybe different times. This way, you can then tear apart your application and put it on a big server if you want to. Have a powerful expressive programming language that allows you to restructure areas as they arise. We've been restructured lots of code in Eve. We've seen, oh, no, this actually can be two services. You can split them apart. And we can do this with minimal effort because we have this powerful programming environment. And you have to design scalability into your framework. Design your software as a service-oriented architecture so that services can run independently of each other. Build RPC, remote procedure calls, and a transparent layer for talking to a server over the network. Build it into the framework from the ground up so it's a natural part of the framework. So you're not scared to make a remote call to a separate machine. And here maybe the most important part is to use your database and design it wisely. You want to be one step ahead. You don't want to drive the database at 100% CPU. You want to be lower than that because one day there may be more users and you want to have a little bit of headroom in there. And you want to stay ahead of the curve. And you should, if you aren't using a database, you should. This is very important. Now, I'm going to show you the final movie, and then we'll have a QA session if we have time. This is our latest trailer for an incursion for expansions that is being rolled out in several steps as we speak.
Vanquish your fear and commute your flesh to dust.
this movie was, yeah. This particular trailer was showcasing the new avatar technology that we're rolling out. But now we have time for some questions. So you can ask me, Phil, where are you? My colleague Phil will come here, and if you have questions in Chinese, he'll translate them for me. We have 5 minutes.
The central database that will be used in vision by whenever
we will throw hardware at the problem. Yes, it will become a bottleneck. We have been lucky in that we have managed to, let's say we've been lucky enough that we have not grown faster than hardware has allowed us to. We are constantly a little bit behind we can get better databases. It's just a question of money and hardware, really. But sometimes we have been close. But like I said, we have to be smarter in the way we use database, and hopefully we won't hit a brick wall there now.
You have 300 servers running at the same time. How do you do the load balance among them?
That's a good question. We try to figure out from each, the game runs 24 hours, but we have a downtime every day, so we turn it off and restart it. We use statistics from every day's run to see which solar systems were most, or how they were visited, and which services used such and such CPU. And we rebalance every day by saying, okay, we can group these together and put them on that server and so on. We have some super servers that are used for particularly demanding jobs like fleet fights and so on. And these are sometimes manually assigned stuff to them. So that, for example, if some players say, we are going to have a 1,500 people fleet fight, can we have this server? Then the game masters can remap a solar system to that particularly powerful server and do that. But we have automatic remapping of services and planets, and we have manual remapping that can be done on the fly and also during downtime. More questions? No questions? Okay. Yep. DBAs. Jon says we have 4. So, okay, I must have provided you with all the information you need. I hope that doesn't mean that there will be a few Eves jumping up here from China next year. All right. Well, thank you very much. You can visit my blog, see all this stuff here, read all about Stackless Python, and develop great games. Bye-bye.